All right, these are the notes from 3.1. The title of the section was Critical Numbers in Extrema. I'm just going to kind of put them on here, so pause as you need to copy it down. The first thing that we did was this graph. Okay, kind of complex. It's got lots of highs and lows. And we labeled each of the x values with one of these different letters, and then of course its corresponding y value name would be the function notation, f of a, right, for the y value at a. Okay, and so then what we talked about was the difference between these two types of extrema that we have. We have global extrema and then we have local extrema. Okay, now global has a synonym, sometimes we call it absolute. Local extrema, which means the highs or the lows, also has a synonym, sometimes we use the word relative. So these two words are interchangeable here, and then global and absolute are interchangeable with one another, but not within these two columns. Okay, so the global, of course, means the biggest function, or the biggest y value that we see over the graph, over the interval that we have. So the highest this got was f of a, the lowest that it got was f of d, and then over here, our local extrema are f of c, okay, our f of e, those are the two little high points, and f of h, we're actually going to consider one. I'm not so worried about you understanding the f of h thing right now. But let's make sure that the local minimums you recognize, that f of d, right, this is a case where an absolute min is also a relative minimum. You'll notice that was not the case with the global max and the relative max. F of a was not a local max because there's nothing on the left side of it to compare it to. Okay, so take a look at those. We did a couple definitions here. Critical numbers are x values where f prime equals 0 or does not exist. And then we also indicated the endpoints are the x values at the end of the given interval. So here our endpoints are a and I. Okay, and then the first task that we had to do was to find the critical numbers. So we looked for places where the derivative was equal to 0. In this case, it was a polynomial function that was given to us, so we simply took the derivative, set it equal to 0, factored it, wrote down our two solutions, and listed two critical numbers as 0 and 1. Okay, these are potential places where there could be extrema. That's why these critical numbers are really important to us. Okay, next example was a quotient, x squared plus 1 over x. Okay, so we talked about how to find critical numbers from a quotient, right? This chapter, in chapter 3, we're going to simplify a lot. So in chapter 2, I said you didn't have to simplify this quotient rule. Now it's very important that we do. So to find places where the derivative equals 0, I take the numerator of the derivative, of the simplified derivative, set that equal to 0. I take the simplified denominator and put that equal to 0, and you'll notice I get 3 critical numbers from that work there. Okay. The next and second thing that we did was finding extrema. This is when we actually find the y values, and here's a step-by-step list of everything we do. The first thing we do is find critical numbers. That's why we practice that to begin with. Then we evaluate f at the critical numbers. Then we check f at the endpoints to see which values are higher or lower, and then we just kind of declare what our max and min is. So example 3 says to find the extrema. This is I'm not sure if you can see this. It says 2x minus 3x to the 2/3, and the interval is -1 to 3. So these are the endpoints that we're talking about in step 3. Okay, so we take the derivative. We go through some nasty simplifying because it is kind of complex. We want to actually subtract these two things from one another. We have to get common denominators and write a single numerator with a single denominator. Now I set the top equal to 0, the bottom equal to 0, and these are my critical numbers 0 and 1. So the next thing I do is evaluate f of 0 and f of 1. That's step 2 from up here. And then I do step 3, okay, where I plug in the endpoints here and here, okay, and I get these 4 values. This one we had to estimate. Okay, but it turns out that it's not any less negative than -5, which is our minimum, and 0, that's the highest of all the y values, that's the maximum. Okay, so we just kind of finally wrote our final answer like this. And then example 4 was a trig problem for everyone to try on their own. So this is 2 sine x minus cosine 2x, the interval 0 to pi. And the only thing you would need, once you take the derivative, it's important to note that for sine of 2x, we did do a substitution using a double angle formula. So we wrote sine of 2x as 2 sine x cosine x. Okay, but then we factored so that we could use the zero product property, and we set each part equal to 0 and solved on the interval 0 to pi only. That's why this guy has no solutions, because we're outside of that domain where sine x equals -1/2. Okay, we take our critical number, we had only one, we plug it into the function, get an answer. We take the endpoints given to us, we plug them into the original function f, we get answers, and whatever's the smallest is our min, whatever's the biggest is our max. Okay. Very last thing we looked at was the extreme value theorem. This is the third of the four theorems that we study. So we took this function 4 minus x squared and we graphed it over these four different sets of intervals. This one was -2 to 1 with brackets. Then we had -2 to 1 parentheses, and we had 1 to 2 and 1 to 2 here. So a little bit different graph. We listed the max and the min for each picture. So the max here is 4, the minimum value is 0. Again, we're referring to the y values, how high it gets and how low it gets. And then the max here is 4, but now it has no minimum because of this hole at -2. Okay, so we say none there. C has no max, but it does have a min of 0. And D has neither a max nor a min because both endpoints are open intervals. Okay, so the extreme value theorem, if you look here, the only one of these four that actually has a max and a min is the closed interval here, -2 and 1. It did indeed have answers for both. And that's exactly what the extreme value theorem states. It says if f of x is continuous on a closed interval, right? It doesn't even have to be differentiable, just continuous. Then we guarantee that f has one maximum and one minimum. Okay? So pauses, you need you to go back and get those notes clear and kind of go a little bit slower and make sure you understand step by step what it looks like we're doing on the paper.